Okay. So that was the third test we were talking about. So it is a direct comparison test, or you can just say comparison test for, again, positively defined series. That is why, as you can see here, the general term of those series, which has general terms an and bn, as you can see here, are positive defined, are greater or equal to 0. And here we have also a relation for direct comparison test. We have a relation between those general terms of the series. So it is, if we suppose that an is smaller or equal to bn for each n positive integer, then we have that test which says if the series which has bn as general term converges, then the series which has general term an also converges. And the second step of that theorem is about divergency. If the series with general term an diverges, then the series which has general term bn also diverges. It comes from just because of that direct comparison between the general terms of the series an and bn, respectively, like that an is smaller or equal to bn. And we already give the first example, so I will continue by the second one and the third one for direct comparison test. So here we will try to find if the sum of 1 over ln 3n from n equals 1 to infinity is divergent or convergent. Again, since on the denominator here you have the ln function, you know that it is positively defined. So you can apply one of the tests that you have seen until now. Here we will use direct comparison test for that positively defined series. So we will start by comparing ln function with x, ln x and x. So we know that for x values which are greater than 0, ln x is always smaller than x. So if you just apply it for 3n here, for each n positive integers, so you can have this inequality which says ln 3n is smaller than 3n. Then 1 over, that means 1 over ln 3n is greater than 1 over 3n. And we know that. Now you try to think about the sum, about the series which has general term 1 over 3n. What you can say about the divergency or convergency. Okay, so what you can say about that series? You can write it as, since 1 over 3 is a constant here, so we have seen that rule, you can write it as 1 over 3 times the sum of 1 over n, right? So this is the harmonic series we have seen last week, or I don't know if we've seen on Monday. That is harmonic series. I guess it was on last week. So we already seen that this is a divergent series. So that makes here the sum of 1 over 3n from n equals 1 to infinity divergent. So when you have that comparison between the general terms of the series that we try to find out, if it is convergent or divergent, and 1 over 3n. So if the smaller one is divergent, by comparison test, you already, you can directly say the sum with general term, or the series with general term 1 over ln 3n also diverges. That is why it says if you have direct comparison between the general terms of two positively defined series, like here, so you have direct comparison, direct conclusion for divergency for second example.
So here's the question. That shouldn't be the case all the time. I can give a counter example if you want.
Can you say again, please?
I can give a counter example if you want.
For second
So
example.
that for that if the larger series diverges, then the first series should be divergent as well.
The smaller one. This is the smaller one. Okay.
So hear me out. Okay, hear me out. Let's say so all the terms of we have two sums. The a sum is sum from n equals 1 to infinity of 1 over n to the power of to the 2 to the power of n. We know that this sum converges, right?
1 over 2n.
2 to the power of n.
1 over 2 to the power of n. So it is 1 over n,
Yes.
1 over 2 times 1 over 2 times n minus 1, which is geometric series. Yes.
Yes.
Okay.
Okay. And the second series
This
is the sum.
This is convergent,
This
by the way.
this is convergent. Okay. So the second series that I want to talk about is the sum of the natural numbers. So the sum from 1 to infinity of n.
Okay.
Okay. We
It
know
goes to,
we know that yes, we know that every term of the first series is smaller than every term of the second series. But because the second series converges, that doesn't because the first series diverges, that doesn't mean that the second series should be divergent as well. We know for a fact that it is convergent.
bir dakika, 1 minute. That one is convergent, but you compare with the natural numbers, right? So all the
Yes.
terms, even you can write it as 1 over 2 in that way on the beginning, because you have the constant there. 1.
So
Okay.
it satisfied all the so they are both positive series. They are all the terms are positive. One is larger than the other, but one is divergent and one is convergent. So they shouldn't reflect conversion or diversion of each other.
But here, the series that you give as an example for geometric series, right? The terms are less than
Small.
the other one. But here the
Yeah,
condition is the opposite.
yeah. I'm saying that B is the natural numbers and A is the geometric series. So because the natural numbers are exclusively larger than the geometric numbers, right? But
Then you
one is
compare the
convergent and
terms,
one is
okay.
divergent. Yes.
Here,
How
let
does
me
that fit in?
see. But the condition is this is the one, right? You know that it is convergent.
This is the geometry, yeah. It converges.
And Bn is geometric series that you talk about.
No. Bn is the natural series.
Yeah,
Is
natural
the natural
series.
numbers.
Natural numbers.
An is the geometric numbers.
But the theorem doesn't says if An is convergent, Bn converges.
No, it says if Bn is convergent or
okay.
divergent.
If Bn is convergent, then that makes An, the series An is convergent.
And if Bn is divergent. Oh, okay. Here, if An is divergent.
The
Oh, I
opposite
see.
case. Okay.
Okay, now I see it. Okay, now
Okay.
I see it.
I am just
So
I need some more coffee, I guess. But I thought it is the opposite condition. Here, if the sentence which start with if is your hypothesis. So it should be satisfied. But for this case, it is the opposite. I hope everyone understand.
I see it now. Okay. Thank you very much.
No problem. Arkadaşlar vallahi ben de herhalde tam ayıkamadım şu anda ama şöyle söyleyeyim. Cümleyi kurabilecek miyim? Ters bir condition var. Yani burada kullandığımız doğal sayılar kümesi söyleyeyim. Sonsuz bir seri 1 artı 2 artı diye giden bir seriden bahsediyoruz burada. Doğal olarak bu sonsuz. Ama karşılaştırma yaptığımızda bizim condition'ımız divergence için küçük olan diverge'e büyük olan diverge olduğunu söylüyoruz. Yani burada aslında bu an küçük eşit bn artı mesela birinci için konuşacak olursak büyük olanın yakınsak olması lazım ki küçük olan yakınsak diyelim. İkinci koşulda da yani bu ilk cümleler, if ile başlayan cümleler yine sizin hipotezlerinizden biri olacak. an küçük eşit bn dışında. İkincisi için de divergence için de sadece şunu söyleyebilirim. Küçük olan yani genel terim küçük olan seri ıraksaksa büyük olan seri ıraksak oluyor. Burada Usama'nın sorduğunda bn diverge olayı var. Yani öyle bir şey yok buradan. Çıkarım yok. Yani direkt şöyle aklınıza tutabilirsiniz. Zaten direct comparison test denmesinin sebebi o. an iki tane pozitif tanımlı seri var elinizde ve genel terimler arasında direkt bir ilişki var. an küçük eşit bn olarak mesela burada verilmiş bu ilişki. Küçük olan yani genel terime daha küçük terimler olan ıraksaksa doğal olarak daha büyük terimlere sahip olan yani daha fazla orada terim daha büyük bir değer olan bn serisi de doğal olarak ıraksayacak. Tam tersi için de bu sefer terimleri daha büyük olan bir infinite seri bir s'ye yakınsıyorsa doğal olarak terimleri daha küçük olan an serisi de yakınsayacak. Oradaki örnekte sadece hipotez yanlış düşünülmüş. O yüzden başka bir durum yok. Devam edelim. Let's give the third example for again direct comparison test for positively defined series. So the general term here is 1 over 2 over n plus 1. So you can directly say that okay, we can compare it with the geometric series because we can write here first by comparing by 1 over 2 over n. So this will be smaller than 1 over 2 over n for each n. And also you can write here the general term of geometric series as 1 over 2 times 1 over 2 over n minus 1. So that means your common ratio r is 1 over 2 and the absolute value of r, or r is in between, minus 1 and 1, which gives from geometric series that series should be convergent, even you know what it converges. Anyone who can say, are there anyone? That is equal to actually the sum of 1 over 2 over n from n equals 1 to infinity. Are there anyone who can say what value it equals?
2.
Yes, 1 over 2 over 1 minus 1 over 2. Yeah, it is 1, no? 1, I guess, no?
Oh, right, because we start from 1, not start from 0. Yes, it's 1.
Here a is 1 over 2 and r is 1 over 2 again, and it will approach a over 1 minus r, so it will be 1. So the sum here is equal to 1, the geometric series. So you need to again be sure that you have the right comparison between the general terms of the series. So the one that you found, which is convergent, has general terms which are greater than the one that you want to find. So this is the right comparison. So you can directly say by direct comparison test, Also your series, which has general term 1 over 2 over n plus 1, also converges. Teşekkür ederim. Thank you, Usama. And now here we have 3 more tests for positively defined series. The third one, I guess this will be the fourth one, is limit comparison test. So let the series a and bn are positive, positive sequence. They just write it as sequence, which means the general, if you have general term an for your series, that makes that series positive. And we have these 3 conclusions. The first one is if the limit of an over bn is equal to L, so which is a finite number, and bn, the series bn converges, then that gives the series of an also converges. And for divergency, if bn here the series bn diverges, then that gives the series of an also diverges. So that means if you have how you will apply this test, for examples, for the ones that we will see here, we will try to find another series that you can compare, or you can just have this quotient which has a finite limit. And also, of course, the other case here should satisfy for conversion. For convergence, bn should be converged. That gives an converged. Or let's say directly, bn an has the same behavior with the bn if you have finite limit, or if you have the limit here. Okay. And second one, if the limit is infinity, which is infinite limit, then that just gives, if bn diverges, that says an also diverges. This is the second case for the theorem. And the third one, if that limit of an over bn is 0, then for divergency, if bn is divergent also, then that gives your series an is also, convergent. If bn is convergent, then that gives your series an is also convergent. So you have these 3 conditions. First one, the equation should be a finite number, and in that case you have the same relation, so you can find the behavior of the series an directly from the series, the behavior of the series bn. The second one, if your limit, that limit is infinity, then, and also if you say bn is divergent, that gives you an is divergent. The third one, when that quotient, the limit of that quotient is 0, and if the series bn convergent, then that gives the behavior of an is also convergent. Let's give examples for this one. The first one is the sum of 1 over n cubed plus 5n. So let's start from this one. We know that the sum of 1 over n cubed is p series. We have seen that on Monday. And p is here, the p is 3, which is greater than 1. So which gives that series, p series, is convergent. And if we compare, if you divide R series, or the general term of R series, by 1 over n cubed, like here, and when we take the limit at infinity, it gives us 1, which is a finite number, and from the theorem we can say that those two series have the same behavior. So we know that this one is convergent. So this is what we call Bn on the theorem. Bn is 1 over n cubed. So since we know that it is a convergent p-series, now since we find that limit is 1, so it is finite number, so we can directly say also our series is convergent by limit comparison test. By the way, you can find that series is convergent by using another methods that we had seen and now we will see. Okay, so this is the one of them that you can apply for that positively defined series to show it is convergent. Let's see the second one, and as you can see, all these series are positively defined. So again, for the second one, we have the general term 1 over 3 root of n squared plus 1. And here, actually the method is like that here. If you have positively defined series, if you wonder how we pick that series Bn, actually you try to write the same general term, let's say 1 over n cubed plus 5n, by using on the denominator the n which has the highest power. So for the first example, for example, you have n cubed. So that is why it is logical to use Bn as 1 over n cubed for limit comparison test. So for the second example, you can see the one that we will pick is 1 over n over 2 over 3. Okay, so this is the one that we will pick as Bn. And when we take the limit, again, it is obvious that will be a 1 at infinity. So which is a finite number. It is also satisfies the first case of the theorem of limit comparison test. And here we know that the sum of 1 over n over the 3 over 3, here 2 over 3, here p is, as a p series, p is 2 over 3, so which is smaller than 1, and by p test we know that, or by p series, definition of p series, we know that this is divergent. And by the first case of the limit comparison test, we can directly say the series of 1 over 3 root of n squared plus 1 also diverges. We can directly say that. Okay, let's...
We can also use the comparison test.
Yes.
Why should we go to the limits?
It is up to you. You can use. Even we write here, in the previous example, we see that both comparison test and limit comparison test are applicable for some series, for example, for this one. So you can use it. Okay?
I see.
So for positively defined series, you can use all these methods that we have. We will see also. We have seen for the chapter 9.3 and 9.3, and some of the series here can be the behavior of the series can be found by more than one test here. So you can use the other ones also for some of them. For example, here we have the sum of 1 over 100 n times 20,000. So this is again positively defined series. Firstly, here we will try to apply comparison test if we can, and we will compare the general term of our series by harmonic series, the general term of the harmonic series. So you can directly have this inequality, and we have any information from the harmonic series, because again, as we said at the beginning of the course, this is not the right inequality or comparison if you have the bigger series as divergent. Okay, so this doesn't give anything. It doesn't say your series is divergent, so we have to try another test for positively defined series. So since we have seen limit comparison test, let's try it. So again, by using the same idea that I have said for the previous example, you will pick 1 over n as bn. So if you divide an by bn, you can directly say it is a finite number, and which says both the series have the same habit. So if that one is divergent, so since this is the harmonic series, the sum of 1 over n from n equals 1 to infinity, that harmonic series is divergent. So you can directly say by limit comparison test, since limit of an over bn at infinity is finite, you can say the one that you try to find the behavior is also divergent. So the important part of those series is, first you have to check if your series is positively defined. Then after that you have to be sure that your conditions or your hypotheses are true, that makes you to reach the real or the true conclusion. So in this example, you can try comparison test with the series. Okay, so this is the right comparison that you can apply for that example. So you have to compare 1 over 100n plus 20,000 by this series. And also now that one will be the smaller one, which is divergent and which gives the series that we try to find out. This one is also divergent. But here, as you can see here, limit comparison test is more usable to apply.
Let's quick question. I remember that if we add a divergent series to a divergent series, we will still get a divergent series, right?
Not every time.
Really?
It can be zero in some way. There should be an example for this one.
A positive divergent series to a positive divergent series.
Yeah, in that way, yes.
Divergent series. What if we multiply a positive divergent series to a positive divergent series? Do we still get a divergent series?
We are not sure about that. You cannot directly say it is true, I guess, for the multiplication.
I got it. Thank you.
Let me see also. Yeah, it doesn't need to be.
All right. Thanks.
You're welcome. And here, I guess this is the last example, yes, for limit comparison. This is an example for comparison test, but first we will try if limit comparison test does work here. The general term of the series is sine n over n square. And we will try to again apply limit comparison test. So again, by the same reason, we will take bn as 1 over n square, which is p series, also converse. And if we just take limit at infinity of an over bn, which will give sine n, and you know that that limit does not exist, because the sin values for all real numbers are in between -1 and 1, so that limit does not approach a unique number, so which gives it does not exist. So from here you cannot have any conclusion for the limit comparison test, because in that test you need to find that limit is finite number or infinity, or it was, I guess, 1, no? Let me see again. Sorry, 0. When it is 0. So you have those three cases. And here you don't have limit, so you cannot apply the limit comparison test. And now we will try direct comparison test. So again, you have this inequality, sin n is smaller or equal to 1, and when you divide here the inequality by n square, which is positive, you have this inequality, sin n over n square is smaller or equal to 1 over n square for each n positive integer. By comparison test, since you know that P series is convergent, which is the bigger one, which has the general term which is bigger than the other one. So you can directly say by comparison test also the series with general term sin n over n square also converges. So here, for example, limit comparison test didn't work. And the last two tests.
I have a question over sin n.
Okay.
Didn't we say that the comparison tests only work on a positive series, but sin can be negative?
But here for the n values, which are greater or equal to 1 and as a positive integer, it has always positive values. It is for all real numbers that you are telling
Yes,
about. It is
but
true, but our
sin n,
mm-hmm.
since we are like taking the function of sinus,
Mm-hmm.
it can go. It is like periodic, so it goes to the positive
Mm-hmm.
and then goes back to negative. So we can't guarantee that all the values will be positive of it. It will have like negative values.
Yeah, but it is for n, well, n values which are more than 1. Let's see here. Okay, they will be always smaller or equal to 1. So for those values, it is always smaller or equal to 1. I don't know if I can explain.
So we know that if it was sin n pi,
Mm-hmm.
that would be, or sin 2 pi, that would be always like, I think 0, or if we like say sin half of pi, that would always be positive, but it can go to the negative side, isn't it?
Yeah, if you have that pi constant here, yes, it is like that. As you can,
No,
as you said,
without the other
this
way
is,
around. If we don't have the pi constant, we
yeah,
can go to the negative easily.
this comes from the, maybe you remember as mathematics 1, we have that which I don't remember in which chapter, but sin x is smaller or equal to maybe even x when x is greater than 0. Do you remember this one?
So here's my biggest problem. I have taken the course, the first course 3 years ago, so
Okay.
there's a lot of things that I cannot remember.
I don't remember in which chapter. It is about again an important theorem that we have seen. I don't remember the name of the theorem, but if you just check out the first part of the book that we Adams and Essex, okay, you will see that let's say, I don't remember the name of the chapter. Okay. If I will remember, I will tell you, but you will see that. Okay. So that comes from there, this one, this inequality. Sin x is smaller or equal to, I guess, x when x is greater than 0. It should be like that.
Okay.
Okay. So this is the, so it will be the last two tests that we will see for positively defined series. If the series an is ultimately positive series, and if rho, which is the limit of an plus 1 over an, so this is the n plus 1 term of the series, and on the denominator you have the general term of your series, then, so that is why it calls ratio. So you have the ratio of n term of your series by the general term, or sorry, n plus 1 term by the n term. And you have these hypotheses. If rho is greater or equal to 0 and smaller than 1, then that gives your series is convergent. If rho, that limit of your equation ratio, is greater than 1 and smaller or equal to infinity, then that gives the limit of your general term is infinity, and which gives from n test, maybe you remember, it is non-zero, so which gives the series diverges to infinity. And the last case is if rho is 1, that limit is 1, then that doesn't says anything, so that test is inconclusive if your rho is 1. So your or may not be convergent. So you should have those two hypotheses if you want to get some information about your series. So let's start by examples. The first term has general term 2 over n plus 5 over 3 over n. And again, now we will use, for those three examples, we will use ratio test. So we will take the limit at infinity of an plus 1 over an. So if you take, if you try to write an plus 1, it will be 2 over n plus 1 plus 5 over 3n plus 1 over an, which is 2 over n plus 5 over 3n. So if you just rewrite this quotient, you will get that at infinity, the limit is 2 over 3, so which is smaller than 1. So let's see the conditions again. Sorry. Smaller than 1. So that directly gives, if rho is smaller than 1, your series is convergent. So here you can say by ratio test, the series converges. And for second one, also I can say here, if you have I made a factorial on the general term of your series, I can say if it is positively defined and if it has factorial, then you should use generally 20%, you should use ratio test. So if you see that kind of general term, you should use ratio test. Here again, that series in the second example is positively defined. So if we use the ratio test, it will be like that. An plus 1 over an is like that. Okay, so if you use the factorial properties, then you get that second step. And if you just simplify here, the limit will be equal to 2 times 2n plus 1 times n over n plus 1 over n. And we will rewrite it again. And here the denominator is e number, if you remember. And the limit at infinity, 1 plus 1 over n is e number, Euler number. And on back here, here you have on numerator, you have the constant n. So it is 4n plus 2. And if n goes to infinity, that makes that limit infinity. So which has the second hypothesis here. So we have the second hypothesis, and which says the limit of an approaches infinity, that gives. So that is why the series diverges to infinity. So you can say that the series, the second example, diverges to infinity by ratio test. Again, for the third one, you have the factorial, so you can just say it is positive and it has factorial, so I can apply ratio test. Again, you divide an plus 1 by an, so you have the quotient an plus 1 over an here. And again, when you use the properties of factorial, you have this simplification of the quotient that we write here. And if you take the limit at infinity, it will gives you 1. So this is the third condition, third case here. But that says the test is inconclusive if your rho is equal to 1. So if you find out that rho is 1, then we cannot, that means we cannot decide if the series is convergent and divergent by using ratio test. So here we try to find out the behavior of the series. So we already write an plus 1 over an, so which is 2 times n plus 1 over 2n plus 1, and we know this is greater than 1, and which gives you an plus 1 is greater than an. That means your series is increasing. So this is positively defined and increasing series, which gives you the direct conclusion that says your series should diverge to infinity, because all the terms are positive and it is increasing. We show that here for each n, we show that. So you can directly say the third example that we have here is divergent or diverges to infinity. And the last test that we will see here for positively defined series is root test. Again, as you can understand by the name, we will take the nth root of the general term of I series. And if we find out that limit of the nth root of the general term of our series is, they have exactly the same hypothesis is here as we have seen for ratio test, but of the limit value that you take is different. Here you take the nth root of general term an, so nth root of your general term of your series, but the cases are the same. So the cases is like that: if that limit is greater or equal to 0 and smaller than 1, then that gives your series is convergent. If it is greater than 1 and smaller or equal to infinity, which gives the limit of your general term infinity, and also that concludes your series is divergent. And the last one is the same. If that limit is 1, then the test doesn't say if your series is convergent or divergent, so it is inconclusive. So this is the last one for the test that we will see for positively defined series. Usama, I can't hear you clearly. Can you say it again?
Can you repeat the root test? I didn't get it.
Okay. It has the same hypothesis that we have seen for ratio test, but of course the limit at infinity that we will take here will be the nth root of an. That is why it calls root test. So you will take the nth root of the general term of your series, and if that limit has those three hypotheses that we have seen for ratio test, they have the same conclusion as the ratio test. Burada sadece limit arkadaşlar. Aldığımız limit farklı. Ratio test oran testi demek. Yani n+1, n+1. terimi serinizin genel terimi, yani n bölündüğünde oluşan bölümün ne yapıyorsunuz? Sonsuzdaki limitine bakıyorsunuz. Burada bu limit için hipotezler, bu 1, 2, 3 case'lerinde yine aynı. Çıkarımlar da aynı ama tabii ki de aldığınız limit farklı. Kök testinde, root testte de n'inci kökünü limitini alıyorsunuz sonsuzda. Serinizin genel terimini. Ve bu şekilde bulduğunuz limit değeri için yine aynı hipotezler ve sonuçlar geçerli. Ratio testte olan hipotez ve sonuçlar geçerli. Mutlak ve koşullu yakınsaklığa bir giriş yapalım. So our next chapter will be about absolute and conditional convergence. And for the previous section, we will just study the convergence of ultimately positive series. And in this section, we investigate the convergence of other series, which are negative, alternating. So for this case, we first get a positive series from a given series. So why we do that? Because we have many methods that we can see if the series is convergent or divergent. So if we take the absolute value of each term, or absolute value of the general term of the series, that makes our series positively defined. And then we can apply all the tests that we have seen on chapter 9.3. So that is why we have this method here. So let's first define what is absolute convergence. A series with general term an is absolutely convergent if the corresponding series of absolute values converges. So which means the sum of absolute value of an or the series of absolute value of an convergent. If this is convergent, you say your series is absolutely, your series of an is absolutely convergent. Okay, if your series is the series of absolute of an is convergent, that gives you your series, or we call that our series of an is absolutely convergent. So by taking the absolute value, we make the series positively defined. And let's see here. Let's see if, okay, here they don't use any method that we have seen, but no problem. Let's start by the example 1. Here we have alternating series, right? As you can see, it has general term -1 over n times 1 over 2 over n. So for even values, it is positive. The terms are positive, but for the odd values of n, it will be negative. So which makes that series alternating. And the corresponding series of absolute values will be one that you just find by taking the absolute value of the general term. So which will be the sum of absolute value of -1 over n times 1 over 2 over n. So which just makes those negative values positive. So it is equal to the sum of 1 over 2 over n. So this is equal to, you can write it as the sum 1 over 2 times 1 over 2 over n minus 1 from n equals 1 to infinity. So which is a geometric series with common ratio 1 over 2, which is a value in between -1 and 1. That says the series is convergent. Again, that we know it is equal to 1, even that sum is equal to 1. And which directly says here, so you conclude that your series with general term minus 1 over n times 1 over 2 over n converges absolutely. Yani mutlak yakınsak diyoruz. Eğer zaten bu 9.4'te genel terimleri pozitif olmayan, işte dalgalı alternate olan serilerin yakınsaklığı, raksaklığı ile ilgili fikir edinmeye çalışacağız. Bunu nasıl yapacağız? 9.3'te gördüğümüz pozitif tanımlı serilerde kullandığımız testleri uygulamak için ilk önce böyle bir mutlak yakınsak tanımı yapıyoruz. Bu mutlak yakınsak ne demek? Genel terimi A olan bir seriniz var ama bu tabii pozitif tanımlı değil burada genel anlamda. Ne yapıyorsunuz? Mutlak AN'in AN serisinin yakınsak rasaklığını inceliyorsunuz. Eğer bu yakınsaksa o zaman serinize ne diyorsunuz? Mutlak yakınsak diyorsunuz. Tabii ki de bu güçlü bir koşul olacak. It is a strong let's say behavior if your series is absolutely convergent. We will see why after these examples.
So,
I can't hear again.
All right. So what I'm saying is that the geometric series converges to 2, right? What does the absolute geometric
This one is equal to 1.
Oh, to 1. Sorry. Okay. I always begin my series by n equals 0. I'm a computer engineer.
Okay.
Equals to 1. So in this alternating series, what does it equal to? Does it equal to something? Does it converge to something else?
I guess I didn't see your voice so clearly, but I said I can guess you are asking if this series is equal to something, right? If we can find the S. No, we cannot find. So we cannot say. Yeah, no. Now from here, from all the information that we get until now, we cannot say if it is equal to something. Okay, this is equal to 1, that geometry series, but we cannot say this equals, we cannot say what is the exact S that alternating series is equal to.
But we said that it is a convergent series, right?
Yeah, we that just say the behavior. Yeah, of course, we know that it equals something, but we don't have the method that we can find it now.
Okay. So okay. Now you know, like the state of the art.
Yeah,
in the course.
Yes.
Okay.
Okay. Yeah. I said that on Monday, but you were not there. So here on chapter 9.3, and generally also we will have the same thing here, 9.4. The thing that we try to find always about the behavior of the series. So we try to reach if it is convergent or divergent. Generally, the ones that we have seen for 9.2, the harmonic series, geometric series, okay, for harmonic series it was divergent, but for geometric series and what was telescoping series, those ones that we know for some, of course, for some values, we know, or for some hypothesis, with some hypothesis, we know the exact sum. But generally, here, for those 2 chapters we have seen, we just try to find out if the series is convergent or divergent. So we are deal with the behavior of the series actually, not the exact sum, if it is convergent. Tamam, okay. And let's give that one, and I guess I will finish that course for today. So for the second example, we will try to investigate if the series of Sn over is convergent or divergent. So again, by taking the, so let's say the absolute value here of sine n over n cube, so that gives you, it is with that, let's say, inequality, and the absolute value of sine n over n cube is smaller or equal to 1 over n cube for each n. So by comparison test, but I guess it directly gives that the series is convergent, because we have the P series here where P is 3 and which is greater than 1. And by using the comparison test, so since the general, the series with general term which is greater is convergent, then the one that we have here should also converge. And since we take the absolute, okay, even you don't take the absolute value, you know that the series is convergent. But as I said, the absolute convergence is a strong behavior of the series, because you will see that in the next theorem. We will see that on next Monday. It will gives you directly the convergence of the series. But it doesn't says that, the theorem doesn't says if your series is convergent, it is absolutely convergent. So absolute convergence is a strong behavior. If you have absolute convergence, you can directly say your series is convergent. So even you don't take the absolute value here, you get that your series is convergent. Also, after we will see the theorem also, if you take the absolute value of the general term, and if you get that it is convergent, which says your series is absolutely convergent, and that will directly give you your series is convergent. Okay. Burada aslında mutlak almasının sebebi o, almasa da zaten yine serinin bir önceki örneklerde olduğu gibi yakınsak olduğunu söylüyor olacağız. Ama mutlak yakınsaklık daha güçlü bir koşul. Yani daha fazla şey söylüyor bize. Mutlak yakınsak olduğunu, yani mutlak AN'in yakınsak olduğunu söylerseniz bu size direkt AN'in, yani AN serisinin yakınsak olduğunu söylüyor. Ama tam tersi geçerli değil. Yani yakınsak olan bir seri mutlak yakınsak diyemiyoruz. It comes from here actually. So if your series is absolutely, if we let it is absolutely convergent, that gives that your, let's say, your absolute value of AN is equal to S. So we say that it is convergent, and let's say it is S, the value that it converges. And if we try to find out here, if it says the series is convergent. So if we have, and for each n, which are positive integers, we have this inequality, minus absolute value of AN is smaller or equal to AN, which is smaller or equal to absolute value of AN. Then if we take the sum of both sides of that inequality, we have this inequality, and which says the sum of AN should be in between the values that we know, which is finite, because we accept that our series is absolutely convergent. So it should be between minus S and S. And by comparison test, that makes, if it is in between those finite numbers, that says your series converges. So since we say that it is absolutely convergent, so which means that that is convergent. So according to this, that I here, the theorem that I was talking about, we have is, if a series is absolutely convergent, then we can directly say it is convergent. But the converse does not hold, so that means the absolute convergency does not give absolute convergency. So a convergent series may not be an absolutely convergent series. There is an example, counterexample for this. So an example for why the converse of the theorem doesn't hold. If you just think about minus 1 over n minus 1 times 1 over n as a general term of the series, and if you take the absolute value, if you try to find out if that series, that one, is absolutely convergent or not, you can directly say that it is equal to harmonic series, and we know that it is divergent. So that means it is not absolutely convergent. So which means the converse case doesn't hold here. So the strong condition here is absolutely convergent. So if you have an absolute convergent series, you can directly say it is convergent. That is why we will always take the absolute value of try to find out first the absolute of the absolute convergence for the next parts of that chapter, and also the reason that we can use all the tests that we use for positively defined series. Burada bitireyim arkadaşlar. Zaten biraz geciktim. Mutlak yakınsaklık tanımını verdik. Koşullu yakınsak nedir diye tanımını vereceğiz. Bir hafta sonra pazartesi günü. Ve dediğim gibi burada mutlak yakınsaklığı veriyor. Yani direkt mutlak yakınsak bir seriye yakınsak diyebiliyorsunuz ama tam tersi, yani yakınsak bir seriye mutlak yakınsak diyemiyorsunuz. O da bir tane de counter example verdik bununla ilgili. Kaydı durdurayım.